Simplifying radicals. Okay, we're going to start with the definition of a perfect square. A perfect square is a number made by squaring an integer. So we're going to list out our perfect squares, and the way we're going to do that is we're just going to square the numbers 1 through 12. We'll just go through 12. So 1 squared, 1 times 1 is 1. 2 squared, 2 times 2 is 4. 3 squared, 3 times 3 is 9. 4 squared, 4 times 4 is 16. 5 squared, which is just 5 times 5 is 25. 6 squared, which is 6 times 6 is 36. 7 squared, 7 times 7 is 49. 8 squared, 8 times 8 is 64. 9 squared, 9 times 9 is 81. 10 squared, which is 10 times 10, is 100. 11 squared, 11 times 11 is 121. And 12 squared, 12 times 12 is 144. Okay, I want you to pause your video, get your calculator out, and write the rest of our perfect squares all the way through 20 squared. Okay, these numbers are going to be important for you to have available during all of this concept. So even on your homework, I suggest that you have this list out in front of you so you can reference it. Next, we're going to talk about a radical. A radical is an expression that has a square root. Now, there's different types of radicals. We could have a cube root or a fourth root. We could have different numbers right here in this index, but we're only going to deal with a square root, which is what you've probably used before. So what a square root does is it takes a number, let's say 9. Takes a number like 9. Notice that 9 was from the list that we just wrote, so it's a perfect square. And it says what times itself is 9. So what number times itself equals 9? Well, that would be 3. So another one might be square root of 16. What times itself equals 16? Well, 4 times 4 is 16, so our answer here is 4. Okay, here's the steps to simplify a square root, which is what we're going to do today. Number 1, see if the number is a perfect square, and if it is, simplify it. So for example, if I just had the square root of 4, 4 is a perfect square because it's in my list that I wrote earlier. So I would just say, okay, what times itself is 4? Well, that's 2. So if we're taking a square root of a perfect square, we only have that first step and we're done. Most of the problems that you do in this concept, though, won't be perfect squares, and you'll have to go on to step 2 as well. So step 2 says, find the largest perfect square that divides your number. Rewrite the square root as 2 roots being multiplied, and then simplify your perfect square. So that's a lot in there. We're going to do some examples and hopefully it'll make a little bit more sense. So this first one, square root 16, step 1, is it a perfect square? Well, it is because it was in our list above. So we are asking ourselves, what times itself equals 16? And that would be 4 because 4 times 4 is 16. So we're done with that problem. Next one, square root 20. I want you to look back at that list of 20 perfect squares that we wrote down. Is 20 on your list? It's not, so it's not a perfect square. We're going to have to do step 2 with this problem. So we're going to find the largest perfect square that does divide 20. The best way to find the largest perfect square that divides 20 is to look at your list, which I've written mine here at the bottom, and find where 20 would go. So let's see, 20 would be between 16 and 25. So that's where 20 would fit. Now we're going to look to everything to the left. Does 16 divide 20? No. Does 9 divide 20? No. But 4 does. So we're going to break this square root of 20 up into the square root of 4 times the square root of, we have to ask ourselves, 4 times what is 20? That would be 5. So now that we've rewritten the square root as 2 roots being multiplied, we can simplify our perfect square. You should always put that perfect square in the front. It just makes it a little bit more easier. So now we can take the square root of 4, which is 2, and just leave the square root of 5 as is. Okay, with our next problem, we have the square root of 32. So again, look in your list, figure out where 32 would fit. That'd be right here between 25 and 36. And now we're going to look to the left to find a number, the biggest number that divides 32. So 25, nope, that doesn't. 16 does, however. I want you to also notice, though, that 4 also divides 32, but it's not the largest. That's why I start where 32 would fit, and I go from there, so that we don't accidentally pick 4. So, we're going to use 16, and we're going to rewrite our radical as the square root of 16 times the square root of, now ask yourself, 16 times what is 32? Well, that would be 2. Now we're going to simplify the square root of 16, and we get 4 square root 2. And we're done. There's a few more examples, and I'm going to write my perfect squares. I only wrote my perfect squares through 49, since my largest example on this page is square root of 40. So it's not that I don't need the rest, it's just for these 3, they're not necessary. Okay, so square root of 40, so look up at our list. 40 would go right here between 36 and 49. Now looking backwards, we need to find which of these divides 40. 36 doesn't, 25 doesn't, 16 doesn't, 9 doesn't, 4 does. So we will rewrite our radical as the square root of 4 times the square root of 10, because 4 times 10 is 40, and then simplify the square root of 4, so we get 2 square root 10. Okay, next problem, square root of 27. 27 would go right here in my list of perfect squares between 25 and 36, and now I look back, 25 doesn't divide 27, 16 doesn't divide 27, but 9 does. So we have the square root of 9 times, we have to ask ourselves, 9 times what is 27? That'd be 3. And then the square root of 9, we get 3, so our answer is 3 square root 3. Notice that this number that's left back here always stays the same. It doesn't change. Okay, in our last problem, square root 14. 14 fits right here between 9 and 16. 9 doesn't divide 14. 4 doesn't divide 14. So there are no perfect squares in my list that divide 14, so I cannot simplify this, and that might happen to you sometimes in your practice or on your test. So you can either just rewrite square root 14, or you could put can't simplify. Either one works. Next, we're going to talk about how to simplify a square root with a fraction. So number 1, if either the numerator or the denominator, that's the top or the bottom, are perfect squares, then simplify them. If there is a radical left on the top after you do step 1, then simplify it by finding the biggest perfect square that divides into it if possible. If there is a radical left on the bottom, then you must rationalize by multiplying the top and the bottom by the denominator. Note, you may never leave a radical in the denominator. It's just not good form to leave a radical in the denominator. It's fine, though, to leave it in the numerator. Okay, so here we go. First step is to see if I have a perfect square in the top or the bottom. So look back at your list of 20. Is 49 in that list? It is, and the square root of 49 is 7, because 7 times 7 is 49. Again, look back at your list. Is 225 in there? And it also is. The square root of 225 is 15, because 15 times 15 is 225. So that problem was pretty easy because they were both perfect squares, and we're done with that one. Next problem. Can't take the square root of 5, it's not on our list, but we can take the square root of 36. Square root of 36 is 6. Since we could not take the square root of 5, we have to leave it inside the square root. So 6 is no longer in the square root because we took the square root of 36. 5 still remains. This is an okay way to leave our answer. We can have a square root on the top, but we can't have one on the bottom. Oh, I also forgot to check. Can we simplify the square root of 5 like we did in the past few slides? So do any of our perfect squares divide 5? No, they don't. Okay, next, same one, kind of, just flipped. We can take the square root of 36, so we get 6. We cannot take the square root of 5, so we have to leave square root 5 on the bottom. This is not an okay way to leave your answer. Again, it's not a proper form to leave a square root in the bottom. So we're going to multiply the top and the bottom by square root of 5. The reason we can do this is because this is actually just the number 1. Anytime you have something divided by itself, it's just a 1. So we're really just multiplying 6 over square root 5 times 1. It just happens to be we would like to use this form. And we will see why in just a second. So on the bottom, we have square root of 5 times square root of 5. 5 times 5 is 25, so we have square root 25. And the square root of 25 is just 5. On the top, we have 6 times square root 5. We just put those side by side, and that means multiply. That is our final answer. Okay, in our last one, we can't take the square root of 6 or 11, so we're going to have square root 6 over square root 11. Again, it's not proper to have this square root in the denominator, so we're going to multiply the top and the bottom by square root of 11. Notice up here on the top, whenever I took square root of 5 times square root of 5, I got just 5. That's how it's always going to happen. So on our next example here, square root of 11 times square root of 11 is just 11. And then on the top, since they're both in square roots, I can go ahead and multiply 6 and 11 together. So I get the square root of 66. And there is my final answer. Okay, here's some more practice problems. Square root 7 over square root 2. I can't take the square root of 7. I can't take the square root of 2. They're not perfect squares. So I'm going to rewrite it as square root of 7 over square root of 2. I cannot leave this radical in the denominator. It's not good form. So I'm going to multiply the top and the bottom by square root of 2. The reason I'm picking to multiply by square root 2 is because what happens here in the denominator. Remember, whenever you have a square root of something times the square root of itself, you just get what's on the inside. And then on the top I have square root 7 times square root 2, so I get square root 14. Now we want to check and make sure, does the square root of 14, does it simplify? Looking at my list here of perfect squares, 14 would fit in right here. 9 doesn't divide 14, neither does 4, so the square root of 14 does not simplify, and this is my final answer. Next problem, 181 are both perfect squares that are on our list, so we can just take the square root of them. The square root of 100 is 10, and the square root of 81 is 9. Make sure that you simplify that fraction if possible. Okay, next problem. 10 is not a perfect square, so it stays in the square root. But 169 is a perfect square. The square root of that is 13. And there's my final answer. I can't simplify the square root of 10 because no perfect squares divide into it. And our last one, square root of 25 is 5 over square root of 6 does not simplify, so we're going to leave it as square root of 6. I cannot leave a radical in the denominator, so I'm going to multiply the top and the bottom by square root of 6. On the bottom, I just get 6. On the top, I get 5 square root 6. We can only multiply the 5 and the 6 together up there if they're both in the square root. If not, we just put them side by side. Okay, pause your video and work out your independent practice problems. Restart your video to see my work. For the first problem, I got 2 square root 3, and the second problem, I got 5 square root 3. In the first problem here, they were both perfect squares, so I just took the square root of each and got 3 over 2. In the second problem, I couldn't take the square root of 6, but I was able to take the square root of 25. And my answer is fine this way because the square root is left in the numerator, or in the top. In both of these, I ended up having to rationalize the denominator because there was a radical left in the bottom. See the red radical in both? For the top one, I just put 10 square root 7 because they were not both in the radical, so I couldn't multiply them together. In the bottom one, however, I had square root of 30, 3 times 10, because they were both in the square root.